In part C of this question, we're getting a pretty sophisticated analysis here of the setup. We're asked about the frictional force and the dependence of the frictional force on the speed, the difference in speeds between the two surfaces. So it's assumed that the frictional force between two surfaces is independent of their relative speed. The details of the axle's construction are unknown, and it's possible that torque depends on the platform's angular speed. So we'll need to delve down a little bit closer in terms of what they mean about the axle and the disc. So here we have the axle, like so, with the disc. And really what they're saying here is that if the way this thing is constructed, we don't really know what's going on at the interaction between these. The friction that's causing the disc to slow down has to do with the interaction between the axle and the disc. So if there's friction between the two of those, they must have different speeds. Either one is stationary and the other is moving, or they're both moving at different speeds. And we don't know what the construction is like, and that also means that it could be just one inside the other and there's grease. It could mean that there are bearings. It could mean that there's a coating of like Teflon or something that has very low friction to reduce the friction. Or it could be something that's designed for it to slow down, something with high friction. So we just don't know about the nature of the construction there. So the question they're really asking is does the speed difference, the omega of this and the omega of this, are they different from each other? And how different from each other they are, does that affect the amount of friction we see? Now, we might expect that as we're speeding this thing up, that the axle, if anything, would have a greater omega than the disc, because the axle is what's driving it. And so if there's very high friction, the omegas will be close to each other. And if there's low friction, well, the axle will have a much greater omega than the disc. So let's say the axle has 2 omega and the disc has 1 omega. But then when this thing is slowing down and it's no longer being powered and the disc is allowed to slow down and come to a stop, well, what we know then is that the axle must be less than the disc. So there's something going on with the interaction of these that will determine the overall acceleration. It might even also be possible for the axle to still be going faster than the disc. It's just not fast enough to maintain the speed that was there before. So it's complicated. We could have everything from the omega of the disc being, or the axle being 0, to it being still greater than the omega of the disc. And we just don't know in that case. In fact, it could even be going in the other direction. Not only is it 0, it could have a negative omega. And so there's a range of possibilities there. But the question is, did the experiment, does it depend? What assumption are we making in this particular case? And I would steer us back and say, let's look at the equation we used to begin with. What we said was that the torque, the frictional torque, is it's I alpha, and the I is proportional to mr squared, and the alpha is delta omega over delta t. And so this delta t is the period of the disc. The change in omega is the omega of the disc. The r is the omega of the disc. And the mass is the omega of the disc. So nowhere in this design is there any examination of, data collected, or looking at the omega, and therefore the alpha, of the axle itself. In fact, there's nothing in this set of data collected that relies upon or asks us to collect information about the axle. And so this situation can occur, that is the disc slowing down, whether or not the axle starts going in the other direction is 0 all the way up to still being greater than omega. We just don't know what the construction is or what the event is. So it does not assume that the torque is independent of the platform's angular speed. Moving on to part D, how could we modify this to determine whether the frictional torque stays constant as the angular speed changes? So if we have the frictional fork itself that's going to change, the frictional torque, is it the same with constant angular speed? Well, if we have a constant frictional torque, and the moment of inertia, which is a function of mr squared, m doesn't change, r doesn't change, then if the frictional torque were to change, that means the alpha must change. And the alpha is delta omega over delta t. So if we examine our graph from part B, we could have this situation going on here. We said that the slope of this graph is alpha. Well, if the alpha is constant, if this is constant, then the torque is constant. Meaning it doesn't matter how fast it's rotating. It doesn't matter how large omega is. It is going to have a constant alpha, which means the torque must be constant. Now, if the torque were increasing with higher omegas, were greater, in that case we would have a steeper slope when omega is large, and as omega got smaller, the slope would decrease. And so this would be the case where alpha, the frictional torque, excuse me. So in this case, the alpha is, the tangent being the acceleration here, the alpha is decreasing, which means the frictional torque is decreasing. Or if it got faster for some reason as alpha increased, it would look like this. In that case, alpha would increase, which would mean that the frictional torque would increase with decreasing omega. So there's 3 different possibilities here, and the point is that this tells us if it's constant, this tells us if it's increasing, and this tells us if it's decreasing. So do we need to redesign the experiment to do this? And the answer is no. And we need to be explicit about that. It does not need to be changed. And what we need to do is do careful analysis of the slope, to determine if alpha is constant, increasing, or decreasing. Torque is directly proportional to the alpha. If alpha is constant, then torque is constant, and then we would go on to explain these other 2 cases. And we could use a sketch to explain that as well.